Okay. Hello, everybody. Today we will continue our sequence-to-sequence model, but we will talk about attention. So this is the idea of our model. We have input tokens, then encoder which can be LSTM. Then we use the hidden vector, the output from LSTM, and use this as input to the decoder. Um, so now let's talk about the idea of attention. And in decoder, we predict the probability of next token. But in different languages, the word order is different. So maybe when we want to translate and predict a new word in French, we translate from French to English in English, then we need to look at the specific word in French. So this is the idea of attention. We can look at all the words in our input sentence, and we need to decide which word we actually want to translate. So we can calculate the weights for each word here. Then we can apply softmax, which will convert these weights into probabilities. And finally, we will get this distribution, which will show us which word actually is more relevant for the translation of the next word. But it's a little bit counterintuitive. Instead of taking embedding for this word, we will actually take all the words. We will sum up these words, but we will sum up these words with these probabilities. And it means that the embedding for the word with the highest probability will be almost unchanged. The other terms will be scaled by a small number. So it doesn't mean that we'll take just one word, we'll take all the words, but the most probable word will introduce larger impact in our sum. So this is the high-level view of attention. So after multiplying these tokens by these probabilities, we sum up and we get the vector. And then we can use this vector in different ways. There are many attention architectures. You can use this vector as hidden vector in the second recurrent neural network. You can use this concatenate with input token here. You can use it after actually a prediction, but before the linear layer, which actually predicts probabilities. So the main idea that we will pass the information about all the words, all the tokens from our encoder to decoder on this step, on each step. So how to calculate these weights? Typically, we denote this by score or attention function. So this is a function between two vectors, between vector from here, decoder, and vector from encoder. And we calculate this function for each vector in encoder. The simplest one is just dot product, which returns one scalar. So yeah, how to calculate. So after we calculate these scores or attention function, we apply softmax and we get probabilities instead. And then we sum up these embeddings with these probabilities. So it's kind of illustration of the previous high-level idea. So the output from attention will be the weighted sum of the outputs from encoder. But I want to go to the slides how to calculate actually this score. So the simplest score function, as I mentioned before, is just a dot product. Well, but in this case, you need to have the hidden vector in both LSTMs of the same size. You can also use different embedding shapes for encoder and decoder. Then you can use this matrix multiplication. Again, if you multiply vector by a matrix, you will get a vector, and then you multiply this vector by another vector. But now you will have some trainable parameters here. And most popular attention mechanism is called additive attention. So I believe there will be a later slide also on this. So we just take a vector from this green vector and multiply by some matrix, let's say W1. Then we take our red vector and multiply by some another matrix of weights, W2. So this is encoder, this is decoder. Then we sum this up together. As you remember, matrix times a vector results in a vector, in a column. So it will be a column. Then we apply nonlinearity. Typically, it's the hyperbolic tangent. And to get one number, a scalar, we apply just linear layer. So this multiplication with weights is the same as applying a linear layer. We apply a linear layer that will map the dimension of embeddings or whatever dimension after this matrix multiplication to one. Just so, and this is called additive attention. But if you concatenate these vectors and multiply it by this extended matrix W1, W2, you can write this sum as just one matrix multiplication. So that's why here we use concatenation instead of using two different matrices. We use so this matrix is kind of the matrix W1 and W2 stacked together. Okay. Okay, I think now we just, well, different architectures. So where we will add attention, the original attention, I just wanted to go to the code, but maybe I can tell about this our main architectures. So the original architecture was proposed in 2014 in the work of Bogdanov, but in English transcription it's pronounced Bogdanov. So this guy was a student of Yandex School, from where I'm using the slides, and then he did his PhD in Mila University in Montreal, and there he actually proposed this idea of attention. So for encoder, he used bidirectional LSTM, and the attention was this with this additive attention. But this attention was used as hidden vector as input in the decoder. So the other attention model proposed next year is called long attention model. The difference here is that instead of using the output from attention as hidden input, it's used before the final linear layer to the size of the dictionary. So it's used on the stage when we want to predict next token probabilities. Okay, so well, why actually how attention works? This is just illustration that in, for example, French economic European, I don't know if I pronounce correctly, but in English it's European economic. So the different order of the words, and here you can see the probabilities. You remember when we calculate attention, first we calculate the probabilities of tokens. So you can visualize these probabilities, and they will show which token from encoder actually like so was taken with highest weight. So yeah, you can see that for um, this word European, it looked not at the diagonal term, but on the other word that actually is European. So this is the idea of attention. Now let's go to the code example. I will just open homework 4 because it's, I believe, hard to understand without actually code how it works. At least it was with me, it was with David also. Um, oh, by the way, in my previous machine learning class, GitHub, you can find actually the solved code for attention. There I just use this for illustration, but I also want to go through the code with you. By default, it's GPU, but because we will just write code, I recommend to switch to CPU to save your GPU time. So the beginning is the same as last time. We upload the data set, which David actually found on Kaggle for French and English. Um, so originally this Bogdanov is from Belarus. Um, another tyrannic regime like Russia, Belarus, all have this um, weird governments. So unzip it. So we create a tokenizer, byte pair tokenizer. And you will see here this tokenizers, one for French, another for English. And I believe in these dictionaries you will see actually all the tokens. Let's see if it. Um, Yes, so you can see also all this, the dictionary with these tokens was saved in this train BP English and French. So we create train and data where we tokenized our phrases and create our vocabularies from these tokens. So input vocabulary stands for French and output vocabulary for English in our case. So we will use the base model from sec to sec. So I just recall that we have some parameters as input vocabulary and output vocabulary. So these are just our dictionaries for English mapping to tokens and French. Then embedding size, you can also change this parameter. So embedding size will be the shape of size of embedding of our tokens. Like for invert to vec, it was 100. Here it's 64. Hidden size is the hidden size, the output from LSTM. Then we had these embeddings. They shouldn't be necessary of the same shape. You can use different shapes of hidden vectors for encoder and decoder, but in this case, they have the same shape from the dictionary size, which is 8,000 in our case. We use BP 8,000 to the embedding size, which is 64 in our case. Encoder is just a simple RNN GRU. So it will just read all the embeddings and return the same number of hidden vectors. Decoder starts. So, for example, if the hidden vector in encoder is different from the shape of hidden vector in decoder, it will map the shape of the output from encoder to the size of encoder. But also, without this additional linear layer, the translation will be worse. So it's also kind of additional parameters for our model. Decoder starts, decoder 0 will be just one cell, not the layer, but just one cell of recurrent neural network, because in each iteration, we will need to also include the attention. So that's why we, and also we need to use the next token based on the probability from the previous token. So that's why we will do this in for loop. And then we translate the output shape to the size of the dictionary. So this is our entire pipeline. Apply encoder to input and provide the translation using decoder. And our main goal is to write this encoder and decoder. So encoder is straightforward. We just apply embedding layer to our inputs and apply LSTM to to this encoding. I don't know, maybe I should illustrate this. So we have input is the batch with some integers, and integers correspond to the tokens in our dictionary. Then we apply embedding layer, so these integers will be mapped into embedding size, and this will be the input to our LSTM. Oh, well, I'm saying LSTM because typically with LSTM for recurrent neural network, in this case GRU. And also there is input hidden vector. I believe it's somehow initialized randomly under the hood. We can initialize by zeros as well. And then this GRU cell will provide the output of the size, hidden size for each. Then this hidden vector will be used as input to the next cell, and it will provide a new output, and so on. So this encoder sequence will be the output of these hidden vectors. And the last, but not really, will stand for the last hidden vector. But as you remember, we should take care of padding. We will take the hidden vector that corresponds to the first end of sequence token. And it shouldn't be the last. So here how we calculate the index for this last but not really position lengths. So we just calculate the index for mask. It's a mask. So if our token is not equal to the end of the sentence token, then it will be 1. Otherwise, it will be 0. And then to calculate the index, we just sum up these ones, and we will get the index. But if, for example, we didn't have padding, then this size will be exactly, it will be equal to the maximum size of our input. And to get index, we should use like the size minus 1. That's why we claim here by shape minus 1 to avoid like non-existent index in our array. Does make sense? So let's say we had like the mask with all ones. Here we had, for example, a mask with ones and then zeros. Then for the first line, the index of end of sequence will be 2, and it's correct. The first 0 will have index 2. But for the last line, the index will be 1, 2, 1, 2, 3, 4, 5. But index 5 doesn't exist in our array because the index begins from 0. That's why we'll subtract in case Um, okay, so this is how we calculate the index of the uh, last but not really uh, hidden vector. And this goes to the last state. So last state, uh, uh, we take from our sequence of outputs from encoder, we take the vectors with index corresponding to the first end of sequence token. Does make sense? So we don't take the exactly the last token, but we take the hidden vectors corresponding to the first end of sequence token. So this will be last state. And it will have shape of batch size times the size of embedding. And decoder start, you remember, decoder start, it was just when we applied linear layer to the last hidden vector to use this as input to the second LSTM. So decoder start, we apply this linear layer to this last but not really output from the encoder. Okay, so this is how encoder works. Do you have any questions about encoder? Okay, decoder is the most complicated part. Um, so for sec-to-sec model without attention, we first read the so let's see. So there is a list. Previous state. Previous state is a list. In sequence to sequence model, this will contain only the output from encoder. But in attention model, it will also contain all the hidden vectors from encoder because we want to use them for attention. So that's why we use list here. And previous token embedding. So the first token will be just the begin of sequence. So we should take the embedding of this token and pass through recurrent neural network cell. So then we will get the hidden vector output from this first. Maybe I should illustrate that. So after you get this hidden vector from encoder, you will use this hidden vector as input to the second recurrent neural network. And the first input token will be begin of sentence for decoder. So, and this dec0 stands for this cell. So the output will be the hidden vector from decoder. After that, we apply linear layer to map this to the size of our dictionary. And these are called logits. So this is one step of decoder. In decode, we should actually iterate and use this output to predict a new word. So in decode step, yeah, we begin with one hot encoder for beginning of sentence. So we calculate these logits from our input that was implemented in decode step. And also we store these logits because later for training, we will use these logits as the prediction and true value of the next word, one hot encoded, like vector of 0 1, as the target and apply cross-entropy loss. And for inference, it will be a little bit different. For inference, we will just take the highest probability from our output logits. Based on this index, we will find token in our dictionary, English dictionary, and then apply embedding to this token and use this embedding as input on the next step. Because for inference, we don't know the ground truth, we don't know the translation. So this is the inference part. Okay, so now we should modify this architecture and add attention mechanism. Oh, we have just 2 minutes left. Okay, maybe yeah, maybe we will then start attention next time because we won't be able to write this for 2 minutes. So the idea is, so we should copy these functions, loss that we created last time. Oh, I also didn't mention about evaluation of the translation. It's called blue metric. Okay. And then we will need to implement this function, this attention layer. And after we implement attention layer, we will just, we're actually done because the rest, oh no, we should also write the attention model. Well, but it will be just additional vector that we will use in our decoder. Okay, so that's it for today. And it looks like the next homework will also extend because I want you to do 2 different models with attention, like long and maybe Bogdanov. We will implement one model, but architecture, but your homework will be to implement 2 different architectures. Just, I hope it will help you to understand this model completely. And after that, we will move to transformers. Stop sharing.